Carts on an incline pulled by a hanging weight. The inclines of Pittsburgh. Even double incline planes. Newton's second and third law, two object problems. Chapter 3, lots of them solved. Let's learn physics. Newton's first law of motion, the law of inertia. All objects at rest will naturally stay at rest, unless acted upon by a net force. All objects in motion will naturally maintain a constant velocity, unless acted upon by a net force. Okay. Newton's second law, it's the equation. Net force equals mass times acceleration. And you could write it down as a sentence like the acceleration of an object is directly proportional to the net force applied to an object and inversely proportional to its mass, or inertia. Okay, that's the second law. Now Newton's third law deals with two objects at a time. Always two objects at a time. Newton's first and second only dealt with one object at a time, but Newton's third law deals with two objects at a time. And the best statement of it is not the whole action-reaction garbage, just crappy language, don't use it. But the two objects always apply same size opposite forces to each other. Two objects always apply same size opposite forces to each other. Because equal and opposite, no, these two forces that are opposite each other are by definition not equal because they're opposite. Because force has a vector nature to it. And if they're opposite, they're not equal. So anyway, two objects always apply same size opposite forces to each other. And a lot of our second law problems require an understanding of Newton's third law because you have two objects pulling on each other, and that internal force between the two is a third law force pair. We don't call it the action-reaction law. Ugh, it's such bad language. We call it the force pair law because they're always in pairs, always in pairs. So this is a series of videos on Newton's second and third laws of motion together. Problems, lots of them. Enjoy. Second and third law, two object problems, chapter 3, all about inclined planes. Let's get those problems solved. And watching this video isn't going to help much unless you stop it and solve that problem independently and then watch through the rest. Check your work. All right, finally we got to the good ones. These are the inclined plane problems. First a single inclined plane, and then double inclined planes and all kinds of fun stuff. But for interest's sake, Pittsburgh has several inclines that still operate. They're designed to work just like an Atwood machine, but on an incline. So this is one view. You actually have this big, huge pulley that runs this one up and that one down at the same time, and they're connected, so they're counterbalanced, kind of like an elevator that's counterbalanced, but on an incline, because a long, long time ago, Pittsburgh had a lot of hills, not a whole lot of people had cars, and rather than run things up and around and around and around, they just ran the thing straight up, and they set it up like this, and it worked out really well. And the other picture looks like this, except it's on an incline. So those two combine to, anyway, it's kind of like an Atwood machine, but on an incline. And you could solve that problem if you wanted to, but here's a quick video of it. All right, so here is a modification. This is kind of a combination of an Atwood machine and an inclined plane and the cart on a flat. Okay, so you got this 2 kilogram cart, no friction, accelerating up in that direction, 1 kilogram mass hanging off on this side, pulling it down. And since this is on an incline, some of the weight is pulling it down the incline, so it's the weight of this minus some of the weight of that, a portion, a component of the weight of that one, pulling it down the incline, and the total mass of 3 kilograms. Similar situation, but you have to draw a free body diagram of an inclined plane. Oh, this is complicated. Anyway, first one you draw, the first force that you draw is the weight. So draw that weight straight down. But before you draw the weight straight down, make sure that you have the x-axis and the y-axis. The x-axis is parallel to the incline. The y-axis is perpendicular to the incline. So x-axis first, dotted, y-axis second, dotted. And then the weight goes straight down toward the bottom of the page. Weight goes straight down, draw it of some length. Weight's 20 newtons. The angle is 20 degrees. That angle is 20 degrees. So as you take this and you lift it up 20 degrees, then the vertical changes by 20 degrees also. So that angle matches that angle. And the 20 newtons at 20 degrees, you find the two components by using your device. 20 cosine 20, enter. 20 sine 20, enter. You get 18.8 newtons and 6.84 newtons for the weight component perpendicular to the incline, pushing it into the incline, and the weight component parallel to the incline, pulling it down the incline. This is the one we're going to want for the initial application. So, what causes the acceleration? The weight of that. What resists the acceleration? 6.84 newtons, the weight component parallel. This tension force parallel to the acceleration on this is the same size as that tension force because, again, this thing doesn't have any friction and minimal mass. So acceleration is net force over mass. You have 10 newtons, the weight of this, minus weight parallel, the opposing weight force, weight component, and then divide that by the total mass of 3 kilograms, and you get 3.16 newtons divided by 3 kilograms, which is 1.05 meters per second every second in that direction. Common acceleration for the two objects. Then you want to find the tension, which is the internal force. So pick an object, pick either this one or this one, and find the tension. I've already drawn this free body diagram, so there's no reason to draw this one, although this one is an easier free body diagram to draw, but if you have it already, why not use it? Forward tension, acceleration's in that direction. Forward tension minus the backward weight component is equal to 2 kilograms times 1.05 meters per second every second. And the tension minus that, add it to both sides, you get 8.94 newtons in that direction. So this is a bigger force than that by the net force. Or you could solve it using the other one. Here is the other free body diagram. Down is going to be the positive direction because that's the direction of acceleration minus the tension. So 10 newtons minus the tension is equal to 1 kilogram times 1.05 meters per second every second. 10 minus t is equal to 1.05. Subtract 10, double negative, 8.95 newtons up, 8.94 newtons in that direction. Same numbers. We're good. All right, here's an inclined plane with friction. I've given you the friction force. It's 1 newton. That says 1 newton. 2 kilogram mass, that's where the friction force is. That attaches to that. 1 kilogram mass hanging over here, 15-degree angle. The acceleration is in that direction on this object and down there. And so same thing, free body diagram. Get used to drawing these free body diagrams. The parallel to the incline, perpendicular to the incline, draw those, carefully draw them, make sure that they match your diagram. This is supposed to represent that object. Free body diagram shows the forces acting on it. So the weight down, and then again, same thing, you're going to take the 20 newtons times the cosine of 15 degrees and the 20 newtons times the sine of 15 degrees. Get the two values, 5.18 newtons and 19.3 newtons perpendicular. This is the one that's important. That's the one that's important. These two help you out if you're going to use that one for the friction force. But I'm giving you the friction force here, 1 newton. Looking for the tension, looking for the acceleration. So looking at this system as a whole, 10 newtons pulling down its weight minus the 5.18 newtons. And don't forget the friction force. 10 newtons minus 5.18 newtons, the weight parallel, and minus 1 newton, divided by a total of 3 kilograms. Subtract, divide, 1.27 meters per second every second in that direction. So up the incline and straight down for the two different objects. Now, if you want to find the internal force, the tension between the two, the Newton's third law pair, from this free body diagram, 10 newtons minus the tension is equal to its mass times the acceleration. 10 newtons minus tension is equal to its mass times acceleration, and you get an tension of 8.73 newtons. Or if you use this one over here, net force, tension minus 5.18 minus 1 newton equals mass, only its mass, 2 kilograms, times the given acceleration, the known acceleration of 1.27 meters per second every second. And you get the exact same value, 8.72 newtons in that direction on this one, in that direction on that one. That is the third law of force pair. Next one, we got two inclines, not an incline and a vertical, but two different inclines. This one's 30 degrees, that one's 50 degrees. I'm going to assume that this thing is going to accelerate in that direction, then come down that way. I'm going to need two separate free body diagrams for the two separate inclines. So starting on the left-hand side, 30 degrees, make sure that 30 degrees is less than 45. That's the parallel to the incline, perpendicular to the incline. Normal force is the same size as the weight component perpendicular to the incline. Tension is forward, acting on that one. Weight is straight down, and again, 10 newtons cosine 30, 10 newtons sine 30, or half. This is a 30, 60, 90 triangle, so half of that would give you this side, and that times the square root of 3 gives you that side. And the other one, the other free body diagram looks like this. You have the weight acting straight down, the weight component perpendicular in that direction into the incline, weight component parallel to the incline. 20 newtons cosine 50 gives you this side, 20 newtons sine 50 gives you this side, and then the normal force is 12.9, the tension is backward. All right, so what's the net force divided by the mass treating the whole system? Ignore the tensions because that's an internal force. That's a Newton's third law pair, internal force. And you want the 15.3 newtons, that's the forward force on this one, minus the 5 newtons, which is the backward force on this one. 15.3 newtons forward, minus the 5 newtons backward. Total of 3 kilograms of mass, 3.43 meters per second every second in that direction. So up this incline, down that incline. And the tension, you want to find the tension, we can use this one or that one, whichever one is fine. Net force equals mass times acceleration. Tension minus 5 newtons, there's no friction. Tension minus 5 newtons, forward minus backward on this one, is equal to 1 kilogram times the constant given common acceleration of 3.43 meters per second every second, minus 5, add 5, 8.43 newtons, and you get the same thing over here. So 8.43 newtons pulling this one forward, 8.43 newtons pulling that one backward. Now here's where it gets a little bit complicated. Hopefully I've solved this one correctly because it does take some time and details to get this right. 1 kilogram mass over here on a 70 degree incline, 3 kilogram mass over here on a 50 degree incline. And make sure that your diagrams match 70 and 50 degrees. It helps a whole lot when your free body diagrams match those things. So we're going to assume that it's going to accelerate in that direction, see what happens. Coefficients of friction. This is, I'm going to define it as a wood block on a wood incline. Grab this little thing here, wood on wood, 0.30 for the kinetic, 0.42 for the static. Makes sense, static should be bigger than the kinetic, 0.42 and 0.30. We're going to assume that it does accelerate and then go back and check and see if it does move from rest. Free body diagram of this one. Oh, look at that, that's pretty complicated. Okay, ignore this part first. This is up the incline, so up the incline is that way. Not quite parallel, is it? Try to make sure that your diagram and yours, your parallel, perpendicular are parallel. Tension up the incline, weight component perpendicular down the incline, and friction opposite that intended motion. So tension's up, weight is straight down, that is 10 newtons. 10 cosine 70, 10 sine 70 gives you 9.4 newtons. And I think that this is going to accelerate in this direction, so I think that the tension is bigger than the weight parallel. So I think that that tension should be bigger than this. Okay, then, friction force. Oh, I know what they are, so I know the coefficients of friction, so I can solve for the kinetic coefficient of friction, coefficient times normal, 0.3 kinetic times 3.42 newtons, because I have the weight perpendicular. And solve, the kinetic is 1.03 newtons. I can also solve for the static, 0.42 multiplied by that same normal force gives me 1.44 newtons. I can use that to check later. Then this one over here, its free body diagram is this thing right there. Weight is straight down, 30 newtons. Weight component perpendicular, 50-degree angle, it should be the smaller one. This should be the bigger one at 23 newtons. There's a tension force acting backward, and since we think this is accelerating in this direction, the friction force would also be acting opposite that intended motion. So here, friction force is left and down. Here, friction force is left and up, opposing motion. So I have the friction force there added to the tension, whereas in this case, it's friction force added to the W parallel. Find those two components, 23 and 19. Normal force is that. Same thing, kinetic coefficient of friction, 0.3 times 19.3, normal force, 5.79 newtons, or 0.42 times 19.3 gives you 8.10 newtons. All right, now, okay, take that whole thing, put that all together. I have the whole solution shown here because it's all scattered all over the page, but look up here. Net force over mass, net force. What's the forward force? Forward force, okay, so just forward force is this. The 23 newtons is the forward force pulling that thing down the incline. And backward force, 5.79. 5.7, what is that? Oh, that's the friction force. So we've got the forward force pulling it down the incline, this thing, minus the friction force, all on this object right here. And then minus 9.40 newtons, minus 1.03. So weight parallel minus friction force, minus weight parallel minus friction force. Got that? So that's all four. Those are the external forces. The tension and the tension, they're double slash, so they're the same size, but they're internal Newton's third law forces. Divided by the total of 4 kilograms, that minus that minus that minus that gives you 6.78, divided by 4 gives you 1.695 meters per second, every second in this direction. So my initially assumed direction was correct. If you get a negative here, that means that it's actually accelerating opposite the direction you assumed, which is fine. Just negative means you're wrong there, or you did some other dumb thing wrong. Then for the to find the tension, the internal tension, I'm going to use, I guess I'll just use this one. This one or this one would be fine. So tension minus W parallel, tension minus W parallel minus friction force is equal to MA. It's right here. Tension is, I don't know that. Weight parallel is 9.40. Friction force is 1.03. Mass of this thing is 1 kilogram, because those two correspond. And the acceleration is the common acceleration of 1.695 meters per second every second. 9.4 minus 1.03 equals 1.695. 10.43, add to the other side. Tension is 12.1 newtons. All right, tension is in that direction. Should be able to solve this. Same thing for tension and get the exact same value using this problem here. But the question is, will it actually accelerate? So let's assume that, well, I don't know. Will it accelerate? So 23 newtons minus 8, which is like 2.5 more, minus 1.44, which is 0.3 more, and the weight parallels would stay the same. So the increase of friction force by using statics instead of kinetics would be about 3, maybe? And the net force is 6.78. So yes, even if it starts at rest, it will accelerate. There you go. Look at that spectacular problem. Love it. If you're on the south side of Pittsburgh, check out the inclines and take a ride. The things are actually pretty cool. The view is really great. These were second and third law 2-object problems. That was chapter 3, final chapter. Lots of problems solved. There you go. Thanks for watching Learn Physics. And thanks for that thumbs up too. Really helps a lot. New videos most academic weeks. Subscribe for more. I've even got education ideas, Freaky Physics Friday, and Tech Tip Tuesday. And for bicycles, motorcycles, and family adventures, it's my other channel, Bike Physics. You just learned physics.